So Nikos, if you'd like to begin, I'll give you a warning when you've had 10 minutes.
Okay, can you see my screen and mouse?
Yes, and your mouse both.
Perfect. So,
and we hear you.
Hello everybody. I'm Nikos Mandarakas. I'm a PhD student in the University of Crete in Greece and working at the Institute of Astrophysics, where we do a lot of interesting stuff, but we really love polarimetry. And this is what I'm going to talk to you about today. So how we can use polarimetry as a tool to search for AGN counterparts of unidentified Fermi-LAT gamma ray sources. First of all, a few words about the Fermi Gamma Ray Telescope. So it operates since 2008 in the gamma ray range and has produced more than 5,700 gamma ray sources. The latest release was in 2020, but we did this work before, so we used the previous data release, which contained a little more than 3,000 gamma ray sources. So the problem with gamma ray sources is the poor localization. So as you can see in your top left plot there is a gamma ray source with its 1, 2, and 3 sigma confidence error ellipses, but it is obvious that it spans across several arc minutes in the sky. And a similar image in the optical, as you can see in the bottom, has maybe hundreds of sources. And it is often very challenging to find the true counterpart of the gamma ray radiation. Now, it makes sense to look for AGN counterparts for gamma ray sources because the vast majority of the identified Fermi sources are actually AGN. So you can see in your right a sky map with all different classes of classifications, and with blue are the AGN. So they completely dominate the identified sources, and particularly 85% of them are blazars. Now, AGNs are, and particularly blazars, of course, are naturally polarized because of the synchrotron emission that can arise in the relativistic jet. But even in the case where there is no jet, in radio-quiet quasars, we can have a polarization due to scattering by the dusty torus that surrounds the black hole. Unfortunately, AGNs are not the only object that can seem polarized in the sky. So, for example, sources that lie behind the interstellar medium can seem partially polarized due to the magnetic fields that trace the interstellar medium. So magnetic fields align the dust within the clouds, preferentially in the perpendicular to the magnetic field, and thus dust grains attenuate radiation preferentially along their major axis, and therefore the background sources look polarized with a polarization angle similar to the projected magnetic field direction. So on your right, you can see the Polaris flare region, a work by Gina Panopoulou and collaborators. And the red lines represent the polarization degree and the polarization angle of the background sources. So from this plot here, it is obvious that there is a trend. There is a distinct pattern that can actually hinder any AGNs or any other naturally polarized sources that lie on the same region. So now, before I go on, I'd like to introduce you to the instrument we used, which is a Robopol, robotic polarimeter, which is mounted in the Skinekas 1.3 meter telescope. And it has the advantage that it is a 4-channel polarimeter. That means that it splits the incoming ray into 4, and we can simultaneously measure Q and U Stokes parameters with a single exposure. So it makes it very fast in comparison to traditional polarimeters. And Robopol's job was primarily to monitor gamma loud blazars, and through this Robopol program, we know that gamma loud blazars are highly polarized, 5% or more even. Now, as I said, there's the problem of the interstellar medium, and this is because we wanted to evaluate the detection efficiency before we test our method. So we used information from the Polaris flare cloud in order to simulate the field. And we used information from the Robopol sample that I just described to simulate an AGN that can lie in this region as well. We carried the simulations, and we wanted to see how many times we could detect actually such a blazar with 3 sigma or 5 sigma precision. And the results are shown in your bottom plot, where in the x-axis you can see the average polarization of the field, and the y-axis is the detectability fraction of these AGNs. So it follows from this plot here that, for example, in high galactic latitudes, where we expect an average polarization of 1% or even less, we expect to have detection efficiency of around 80%. And moreover, we used the polarization data of polarized stars by Halley's and the reddening data from Schlafly in order to find the correlation between reddening and polarization. We applied this to the unidentified Fermi sources, and we calculated that in the case of the third Fermi gamma ray catalog, we would be able to detect more than 500 AGN using this method. So I will present you now some results. We observed 4 different Fermi fields, and in one of them we got lucky and we found such an outstanding source. So this is the field that we studied, that I showed before as well, along with the 1, 2, and 3 sigma error ellipses. And as you can see, there are many sources that can be seen in the optical. And therefore, we measured the polarization of most of them, and we made this nice plot. So on your left, you can see the Q and U Stokes parameters for all the sources in the field. And there is clearly one outlier. So this mark here with, it is marked here with red, and it clearly deviates from the average trend, right? And you can see the same picture on your right, where you can see a histogram of the polarization degree of all the sources in the field. And again, the same source is clearly away from the others with a polarization degree of 5.2%, while the average polarization of the field is 0.91%. Now, here's the field that we studied, as I showed, together with the error ellipses. And you can see our candidate, which is this little spot here, lies just outside the 2 sigma confidence error ellipse. But this is for the third data release of Fermi. And I said now there is the fourth data release, which has twice as much exposure time and a number of analysis improvements. And for example, the fourth data release has provided updated position and better localization for this gamma ray source. And this is the new gamma ray position. And as you can see with red here, our candidate lies within the 1 sigma confidence error ellipse. So I'd like to draw your attention here to the fact that it is very extraordinary that polarimetry was so precise even before Fermi updated their pipelines and could better localize the gamma ray source. So finally, what is left is to confirm the AGN nature of our candidate. And for this reason, we took spectra from the Skinekas Observatory. You can see, as you can see in the top left, we found that our candidate is redshifted. You can see emission lines here, and also we gathered archival data from optical, infrared, UV, and X-ray emissions, and we plot them together with the gamma ray data from the Fermi for this field. And we also found the position of our candidate in the BPT diagram, which is on the bottom.
10 minutes, Nikos.
Yes, thank you. Our candidate is depicted with a yellow star here. So these diagrams are diagnostics for galaxies, and our candidate is very close to the star-forming plus AGN region. So based on all these results, we argue that this candidate is probably a hybrid source, a star-forming galaxy with an obscured AGN at its center, for example. So why is this important? Now, this research becomes very relevant with the coming of Pacify, which is the largest optopolarimetric survey, and it is going to see first light this summer, and it is going to survey millions of stars across the sky. Now, in this plot, I'm showing with blue points all the unidentified gamma ray sources of the fourth data release of Fermi, and with the shaded red region is approximately the area that will be covered by Pacify. So we'll have the opportunity to mine the Pacify data and basically search for hundreds of AGN candidates as counterparts for gamma rays. And this is basically for free because the data will exist and we can easily do this work. So finally, what I'd like you to gather from this presentation as a keep home message is that polarimetry is a very powerful and reliable and very fast tool for detecting AGN, fast compared, for example, to spectroscopy. And it can be extremely useful in this big data era. And it can be useful not only for Fermi, but also, for example, for Gaia alerts. Having information on the polarization by Pacify, when an alert comes up, polarimetric information can be included, and potentially someone could check whether whether an AGN is responsible for the alert. And it was very fortunate that Benny talked earlier about changing look AGNs, and I think this is a very precise example of how polarimetry, in this case, would add this bit of extra information that we would need to confirm that a source is actually an AGN. Thank you very much for your attention, and if you want to learn more on this work or contact me, this is the time for you to take a screenshot, and thank you very much for your attention.
Thank you very much, Nikos. Do we have any questions? I'd like to ask just a very quick question. I didn't understand exactly the specifications of Pacify. Can you, well, I should screenshot and go and look at it. But what is the,
sorry,
is it spectroscopic?
The diagnostic diagrams?
No, your instrument, if I've understood.
So the instrument, Robopol.
I thought Pacify was the next generation. Or...
Yes. So
yes.
we did this work with Robopol instrument.
Yeah.
But Pacify, so Robopol is optimized for single target.
Yeah.
But Pacify will be a wide field survey, and
right.
This is why it will give the opportunity to do so good science.
Right, and why you get the multi-object coverage.
Right, exactly.
Okay, thank you very much for that.